of Environmental Sciences, and thanks for inviting me here. And it's a great opportunity so that I can explain foundation models. It's a very interesting term to all of you. I have been doing AI research since I was a PhD student many years ago, and some of my ongoing projects is about first identifying social determinants of health, different health outcomes, and using AI method to kind of provide better disaster mitigation strategies. So today I'm going to introduce an interesting term, foundation models, and maybe some of you have heard about this term before. So what is a foundation model, right? Probably you have heard about this term, large language model, right? ChatGPT is a typical large language model, and I assume some of you have used that before, right? Raise up your hands if you used that before. All of you, nice. So we call it large language model, but essentially it is a language model, right? But when we are referring to the foundation model, we may refer to the models that are not language at all, right? We can train the model based on pictures. We call it visual foundation model. We train the foundation model based on the text, based on those voice signals, right? We can say it's voice foundation models. So it's not necessary to be the foundation regarding the language. Okay. And the first definition of the foundation model actually comes from the Stanford Institute. So Stanford Institute for Human-Centered Artificial Intelligence coined this term in August 2021. And they're saying a foundation model is a model trained on broad data that can be adapted to a wide range of tasks. Right? So imagine we have all those type of data sources, textual descriptions, images, speeches, signals, and through very intensive model training and through those foundation models, we're able to ask a lot of questions. Right? We can ask a model to give us some sentimental analysis for sentences. Right? Ask a model to extract the key information that you need. Maybe ask a model to do some image captioning, describing the pictures for us. Right? And do object detection, identify key objects in a picture, right? So a variety of different tasks. It means that this model over here is like a general intelligence that kind of answers or responds to your queries, right? So let me give you an example. What's the difference between a foundation model and a task-specific AI model, all right? So when I was a PhD student, my dissertation is about flooding mapping, right? So during the flood events, we cannot rely on satellite images because most of the time it's cloudy, right? We cannot see what's going on the ground. So we have to rely on data provided by the citizens. And during those flooding events, we see a lot of social media posts, those flooding related pictures, right? Those pictures are popping up every second, thousands of them. And we can easily, using AI method, to kind of estimate the water depths in those pictures. And since those pictures are with coordinates, we know exactly where they are, so we can kind of build the entire flooding surface from one single flooding picture, something like that, right? And some of the AI models I use is like this. So if a picture contains a human body over here, then the AI model will kind of segment your body into different parts, different segments, and then it's going to look at which part of your body is missing, covered by water, and then we'll estimate the water depth in this case. So this is very clever algorithm, right? This is very clever algorithm, very clever AI model, but this model is task specific, right? It only works for flooding mitigation purposes. It only works for kind of generating the water depths, right? But a couple of days ago, I tried this. I tried to upload a picture to see if ChatGPT, this generalized AI model, can complete the task for me. So I chose a random flooding model over here, random pictures, uploaded to ChatGPT. I think the version is ChatGPT 4, and then tell the GPT estimate the water depths in this picture. Right? And interestingly, this is answer provided by the GPT. So it has its own logic. I don't know if you can see this, but it says we can use vehicle as a reference to estimating the water depths. And the estimation is about 15 to 18 inches. Or we can use human as a reference to estimate the water depth. It's about 16 to 24 inches. But if we combine those estimations from those two references, the final estimation given by ChatGPT-4 is 12 to 14 inches. So it's kind of accurate, right? It's a valid estimation. So it means that it turns out ChatGPT, this general model, has the basic understanding of a picture. And if you ask this generalized AI to do a specific task, like estimating the water depths, it can complete the job for you. But of course, you can ask a lot of different questions, like how many people in this picture, right? Or what's the brand of the car over there? ChatGPT will also give you the answer. So that's the difference between a task-specific AI model, like the segmentation, like the body segmentation model I built, compared to a generalized foundation model, which understands the core or the essence of a picture that can be adapted to a variety of different tasks. That's their core difference. All right, so where are we now? The term artificial intelligence was coined in 1956. I was not born yet, so at the time, so I don't know what's going on. And 2 years later, we have another new term, machine learning, coined. And machine learning is a higher term compared to artificial intelligence. And you can see we have some very fancy models, Bayesian networks, causal analysis. This very popular model used by many statisticians over there. And this method was developed in 1958. Okay, I'm trying my best. Hello, test. That's much better. Okay, good. All right. So starting from 2015, we have seen a boom in artificial intelligence. So, for example, AlphaGo was introduced in 2016, and then Google introduces Transformer in 2017. And for you, if you are working in computer science domain, Transformer is a very popular architecture, and the first version of GPT is actually based on Transformer. Okay, and starting from 2020, we see a very interesting term coming up, which is LLM, large language model, right? And we all know what happened in 2023. ChatGPT, the third version, ChatGPT 3, was released, and we call it ChatGPT, but it's actually the third version of it. All right. So right now, here we're using the fourth version of the GPT, and actually this version is considered as outdated. Now GPT OpenAI has a new system called. Okay. Hello. Right. So ChatGPT 4 is considered as outdated. We're using a newly version of it, which is ChatGPT 01. This is model newly developed by OpenAI. So, but at what cost? All right. Yes. Yeah. Transformer, for example, we've talked about convolutional neural network, right? It handles visual information very efficiently, and Transformer is something like that, but it handles textual information, like the text. Yeah. So it has multiple hidden layers and organized in a very dedicated way to kind of transform the text description to hierarchical or high demanding embeddings that conveys meanings. Okay. Yeah. So if you look at this figure, we know that the success of an AI model depends on the training data set and also the sheer size of the model. If a model is big enough, it's able to be generalized to different tasks, right? So if you look at this, the first version of the GPT model contains. Hello. Can you hear me okay? Is it better? Hello. Test. All right. The first version of the GPT model has about 117 million parameters, right? But 2 years later, in 2023, you will see that this version of GPT was released, and it has 175 billion parameters. So 1,000 times more compared to the previous version, right? Now we're having this. 1 year later, we have the fourth version of the GPT, GPT-4. Now it has 1.8 trillion parameters, 10 times more compared to its previous version, right? So it's moving really fast. We're building bigger and bigger models, right? But at what cost? Training the GPT, third version of the GPT, with about 175 billion parameters will consume 1287 megawatt hours of electricity. Okay, and we have to emit approximately 502 metric tons of CO2, which is equivalent to the annual emission of 112 gasoline cars. That is our cost. And this is the model we're talking about, the third version of the GPT. But if you look at this, it's 10 times more, right? And the latest version, the GPT-01 version, is much, much bigger. So imagine those are the energy we have to burn out, and it will have a huge impact on our environment. All right, so in fact, not just OpenAI, Microsoft, and Amazon, they're also building their own foundation models. For example, Amazon and Microsoft, they have built their massive data centers to support the training of their foundation models. And in 2014, in fact, all the data centers in the United States consume approximately 70 billion kilowatt hours of electricity. And this is about 1.8% of the total energy consumed across the whole United States, right? And this number is expected to increase to 35 gigawatts by 2030, which is actually double the amount of the consumption in 2022. So imagine, those are the energy we have to burn out. Those are the energy we have to use to support those type of foundation models. All right, so that's some insights, general insights of the foundation model. I want to take a few minutes to briefly introduce another model, which is Geo Foundation model. All right, and the difference between the Geo Foundation model and the foundation model is not that much, actually. So Geo Foundation model is basically the foundation model trained on remote sensing pictures, right? And to answer some picture-related tasks. And if you look at this, since 2023 over here, the release of GPT models, we actually started to build these Geo Foundation models on the top of that. So everything, we're still using the foundation model, but we're training the model specifically on massive Earth observation pictures. And there are a lot of interesting tasks you can do with the Geo Foundation models. For example, you can ask if an object exists in the picture. Is there a swimming pool in this view, right? You can also ask the model to kind of count objects for you. How many cars in this view? How many planes in this airport, right? You can also ask something about the spatial relationships, like please estimate the distance between two different buildings, right? And there are more complicated tasks. For example, change detection. If you provide a picture or imagery 5 years ago and the imagery right now, you can ask the Geo Foundation model to kind of estimate or highlight the changes, describe the changes for you, right? So with the improvement of those Geo Foundation models, we are expecting that those foundation models can do much, much more complicated tasks compared with predecessors. Right, so what does it mean for the future? I have a very interesting applications I want to introduce. I introduced this case to many of my students, right? So in 1962, we had the Cuba Missile Crisis. The Russians, or I should say the Soviet Union, was trying to build up the ballistic missile launching sites in Cuba, right? And the United States managed to get some of those pictures. They're capturing those launching sets, and those pictures, imageries were sent to the interpreters, a large group of people to interpret, and then present those pictures to the President Kennedy. And we kind of return from the edge of a nuclear war, right? But imagine, this is That was 60 years ago when we have to do manual interpretation, scene by scene, picture by picture. Now we have entered a new era with tens of thousands of satellites above us, and they're monitoring every inch, every corner of our planet. They're providing real-time monitoring, real-time estimations, right? But those pictures are just sitting there. We don't have the manpower to interpret them one by one. Imagine if we build this gigantic or robust geofoundation models that can tell us the changes every inch across the space. And this will change everything we have, every aspect of how we understand environment and how we understand our planet. So at the very last page, I want to briefly touch on some methodologies or mechanisms we can make foundation models more efficient. So first, we can improve the model efficiency, like using model pruning, quantization, or knowledge dissemination. Those type of methods are very efficient in terms of reducing the model size. And we can also do some hardware optimization. For example, NVIDIA's Blackwell GPUs use 350 times less energy to train the GPT-4 model compared to its previous version. Right? So in the future, I'm expecting that we'll be using more and more energy efficient GPU or hardwares for model training. And we can do some algorithm developments to make those algorithms more intelligent and more efficient so that our model cannot, maybe we can reduce the size of our model. And finally, we can incorporate and integrate some renewable energy into the training process so that we do not emit that much carbon, produce that much carbon footprint. Right, I think that's all I want to share today. So just a brief introduction about foundation models and their challenges. Thank you very much.
Oh, yeah. Two questions. Yes, sir.
For most of the foundation models, geofoundation models, we train the model using satellite pictures because we have tons of them, right? But you can also, kind of insert those area photos to the foundation model, so it's possible and it's doable. Yeah. Yeah, and some of the foundation models are using drone pictures to train the model. So super high resolution drone pictures can also be inserted to those geofoundation models. Yeah, I think there might be some regulation in the future, considering that we're building models bigger and bigger, right? Imagine ChatGPT 4 is 10 times bigger than 3. 3 is 1,000 times bigger than 1. And for the latest version, 1, we don't have much details, so we don't know how big that model is. But in the future, I would assume that those foundation models will become gigantic, and training them is very resources demanding. So I would assume that in the future, there might be some regulations for training those large models. I think the growth of the model is never linear. So maybe in the future, they will receive a gigantic increase of the model size, right? Transformer was considered as a big leap compared to other models. But now we're having trillions of parameters in just a couple of years. So it's never a linear progress. But if you look at the optimization of the hardwares, it's very linear, right? So I would assume that in the future, there will be a huge imbalance between the sheer size of the model and the optimization efforts in the hardware. So I think this remains to be a big issue in the future.
Thank you so much. out our next speaker is Professor Vijay Madisetti. Did I get that right? All right, cool. He is a professor at Georgia Tech, so we're getting both our Atlanta institutions here today. He's in the College of Computing, and he does cybersecurity and privacy. So he's authored several books, including, I was really excited about VLSI, Digital Signal Processors, which means I might have actually used your book in college, so that was a little exciting there. And the Digital Signal Processing Handbook, but he's a frequent consultant all over the country, but he's here today to talk to us about blockchain and AI. So take it away.
I have a lot of slides, but I will try to. Is it on? Okay, can you hear me? Yeah, okay. These are not my slides, though. How many of you have heard about and understand how a blockchain works? So you do understand? Okay. So I'll go through that for some of the others then. So so let me give you a perspective of what's happening in the blockchain, crypto, Web 3.0 world. As mentioned by Amy, I love writing books, and I've written a lot of books. I keep writing books all the time, and I learn more from the books by writing about them. So there's a big new development. It's called Web 3.0. And what is Web 3.0? Web 3.0 consists of three things. One of them is called the Internet of Things. That means that everything is Web 3.0. The advantage of analytics is that you can now analyze a tremendous amount of data with using large language models. Internet of Things means that you can connect everything to the world, to the web, and blockchain is a technology that allows all this integration to take place. So let us look at how blockchain developed. It started off as a distributed database about 10-15 years ago, where you could store information in a database in a secure manner. But now it has become essentially a distributed computer because we have reached third generation of blockchain. The first generation of blockchain was simply for crypto. The second generation focused on what are called as writing programs on blockchain. The third one is actually where now it scales to millions of users. So that's how the generations of blockchains have changed over the past decade. So if you look at the evolution of the web, about 30 years ago, the web was simply a mechanism by which you could distribute data. So you could sit on your computer and read some websites. Then what happened is that this is the model of the early web. What happened next is that you could start adding software to the websites to do additional server-based processing. And that added more functionality. For example, you could log on and look at payroll or do additional processing. Then what happened is that a lot of companies started developing servers where they started running their own applications. This was the year 2000, where you could run a lot of complex applications on your own servers. And then people changed from writing code on their own servers to writing code on servers provided by Google or Amazon. So this became what is called as cloud computing in 2010. And that is how the world operates today. The world has a large number of servers from Google, Facebook, and others, and everyone else writes applications which run on the cloud. But what has happened is that this is the world that we live in now, where everyone runs applications on the cloud. But what is happening is that it's a new world called this Web 3.0, that is going to completely change the way computing is done. And that's what is the blockchain. So blockchain is the foundation of the so-called decentralized web, which is different from what we are running on right now, where the world is running on data centers with lots of applications running on the data centers run by Google. So let us look at what a blockchain does at a very simple way. Supposing you go to Starbucks and buy coffee, you pay money to Starbucks and they give you coffee. So what happens in the background? You have a lot of banks that are involved, and all the banks are processing the payments, but the physical product is still exchanged between the two parties. So if you look at it in a layered manner, there is a money layer, there's a payments layer, there's an information layer, and there's a product or services layer. All this is still traditional, run by credit cards and by information, but products are still outside that. So what Uber has done is that Uber has changed products, and you're able to now offer services using the same model, where the money and payments and information are supplied by Uber, and you are able to offer your services tied to the Starbucks model. So now you can extend this model to a variety of different types of services. For example, you could rent your home as Airbnb or your car, and all of these form this same model, where you are effectively creating a services layer based on the same payment model. But what blockchain does is completely different. It actually gets rid of those two different layers. You are actually able to exchange not just a service, but also the information directly with others and something called a token. The token is the value that you communicate to somebody in return for a service. You don't require any intermediary. All these three layers are transmitted from one peer to another peer without need for a bank or a government or anything else. So that's the advantage of a blockchain, is that you are creating a technology that allows any two people to exchange things of value without any bank being involved. So that's the beauty of blockchain and the power of the blockchain. It is called tokenization, where everything has a particular token that you can exchange. The token can be a service or it can be some value. So what a blockchain does is that it allows you to trust each other so that you can exchange tokens with complete confidence that it will not be misused. So how it's done is that you set up all these transactions in a chain, and then each chain builds on the previous block in the chain. So therefore, you are able to link together all the blocks of transactions in a chain. And how you do that is that every transaction block a hash is computed that is representative of this set of transactions every 10 minutes. And every 10 minutes, the hash of this is combined with the hash of the next 10 minutes, which is combined with the hash of the next 10 minutes forever. So you cannot change the transactions in any order block without changing every other block that goes before. So that way, you are having a very secure set of transactions that anyone can verify that have occurred and cannot be changed. So this allows you to work very securely, because if you have a bunch of transactions every 10 minutes, all the transactions are hashed together. So if any of the transactions changes, all the hashes of all the future transactions will change, and that creates a problem, because you can then identify that those transactions were corrupt. So this means that if I give some money to somebody on the street, that money, the transaction is recorded on this block, and everyone knows that the recipient has received that money from me, and then they can spend that money without worry, because everyone knows that that person has money that they received from me, and they can verify that on the block. So this becomes a very powerful environment. So the blockchain has a protocol that allows it to compute these hashes, and each hash of the previous block is added to the hash of the next block to make it a very immutable set of data. So the second important thing about crypto and blockchain is that it's called proof of work. So when you look at crypto, somebody has to verify that all the transactions in every block are correct. And that is done using something called proof of work in crypto. It means that somebody has to not only verify the transactions, they have to compute a puzzle and add it to the block. And then computing the puzzle takes a lot of computation. So this means that to change a previous block, you have to recompute that puzzle. And this makes it difficult for you to recompute something because you're adding this difficult task called proof of work. And this proof of work is then computed by a bunch of nodes called miners that compete to compute and validate the transactions before it's added to the network. And finally, more than 50% of the nodes on the network have to validate and say that this particular proof of work is correct. And that means the blockchain then is fully functional. So all these take a lot of energy, they take a lot of time. And as a result, there has been a lot of work on how to reduce the energy consumption, for example, for things like Bitcoin and future cryptocurrency. And the most recent work has focused on it, not just the proof of work, but things like what are called as proof of stake and proof of authority. Proof of stake means that the nodes that have the most amount of crypto are those that are believed in the validation process. So if you have more money, you are more likely to believe in the network, and you're likely to be more believable because you own a stake in the network, so you're unlikely to do something wrong. As a result, proof of stake is much simpler, and it allows you to do it very cheaply, getting rid of some of the energy issues. So the proof of work is now being systematically taken away from the blockchain. So any worries that the blockchain takes a lot of energy is only related now to Bitcoin. Everyone else, all the second and third generation, are moving to proof of stake and proof of authority and so on. So as you can see here, among all these blockchain networks, most of them are moving away from the proof of work. And therefore, there's all the crypto problems with energy are only for the first generation, which is the Bitcoin. So I can go into this further, but there's a lot of stuff that focuses on Bitcoin and the energy, which is right, but that's only the first generation. The second generation is now much more flexible. The third generation is almost the same speed as Visa or MasterCard. So what has blockchain done for you? Blockchain allows you to, each organization has its own data and they don't trust each other. What blockchain allows you to do is allow frictionless processes between organizations by having a common shared database that is trusted and cannot be changed. So getting back to this figure, when you have such a common database, you can exchange tokens with the understanding that anyone can verify the transaction, and as a result, there is complete frictionless peer-to-peer type of transaction. So I can go further, but I can stop here if you have any questions, and because I have a lot of slides on different aspects of that.
Question. I have a question. So you were talking about tokenization and getting rid of it. So what does this mean for like Visa? Do they become?
So what that means is that if you look at tokenization, let me get to that. Yeah. So blockchains in general are a bit slower. Yeah. Blockchains in general are a bit slower. The number of transactions per second is low. On the other hand, so TPS stands for the number of transactions. So if you look at Visa, the number of transactions is something like 200,000 transactions, while for blockchain it's 15 or so. So one of the problems is that when you tokenize things, it's likely that you will be much slower. So what is done typically is that you will offload the transactions from a public chain to a private chain and synchronize with the public chain only now and then. So that way, if you are Home Depot, you would synchronize on the public chain just a few times, but all your customers and transactions would occur in the internal chain much more frequently. So the second thing about tokens is that you can exchange tokens in a much more easier manner than cash. So if you're trying to exchange your home in return for rental of a car, your tokens could carry out the transfer and exchange without worrying about a common money. Yeah.
I'm sorry. I don't think that's a fair representation anymore. Like Solana is like 50,000.
Yeah, Solana is 150,000 and all that, but this was more for the Bitcoin.
Got it.
Bitcoin. Yeah. Solana is much faster.
Yeah, but the debate about that is Solana is like centralized, more centralized.
More centralized. Yeah. So the problem right now is that, so there are many problems with blockchain that we are trying to solve. The first one is identity, because it's anonymous. So if Walmart has 6 blockchains, the same person has 6 different accounts.
Right.
And also because of anonymity, there could be problems with laundering and drug trafficking. So the question now is, how do you connect the blockchain accounts to the real world? That's a big problem. The second problem is, even Walmart has 6 different blockchains. How do you make them interoperable? Everyone is writing their own blockchain. JP Morgan is writing his own blockchain. So that's the second problem. The third problem is scalability. Because blockchains are expensive and all that, how do you make them fast? So people have looked at a variety of offloading, level 2, and all these others. So there's a lot of research that's being done. So effectively, what is being done is, for example, this is something called a value token transfer protocol, which is similar to HTTP, but it operates on tokens. So it allows 2 different blockchains to exchange tokens instead of like HTTP. So there are so many different types of things that you can do. And the problem is that it's always a trade-off between security, centralization, and performance. So if you go to Solana, it is centralized a little more, but higher performance. If it's completely decentralized, then you have more security but less scalability. So all these sort of trade-offs. So we came up with this sort of thing, and how this sort of triangle where you choose between those 3 different choices. And it's a different. So there's a lot of stuff that I do in the area of blockchain, and I've been filing almost 1 patent every month. And each time there's a new problem, you get a new solution. And so it's been a very fertile area for that. Yes.
Can you talk a bit more about sustainability?
Yeah. So the key is that when you look at these various blockchain platforms, the biggest problem has been with consensus. That means how do all these nodes agree to put something on the blockchain? And previously it has been the proof of work, which was the problem with Bitcoin. But most of the others are now moving to the more efficient proof of stake. So that we feel now has removed that problem completely from crypto. Even though Bitcoin, yeah.
I'm here not because I care about that. I care about the sustainability of energy consumption issues.
and the gas that Georgia Power is holding to the rest data center growth in the state, and Virginia, North Carolina, and so on. So you're going to just really focus on that part.
Yeah. So as long as I know Georgia Power is doing a lot for Bitcoin mining and everything else, so that would be the problem that they can't solve, because Bitcoin uses the proof of work. So unless you can change the protocol and go for a proof of stake, that will continuously be a problem.
So here's how it looks to me.
Yeah.
Georgia Power, Duke Energy, Progress, NextEra, all those utilities think that data center growth needs are urgent, but climate change is not urgent. And so that's what's really bothering me. That's why I'm here tonight.
No, I think so that there are other options like nuclear power, like other sources of energy. For example, data centers that use geothermal power and others, they could be good solutions as opposed to the traditional coal-fired type of heat generation. The second is that much of the data center growth is for the AI. It's less for mining anymore, because mining is now being done by dedicated chips, which consume much load.
So I guess the question is because there has been a ton of Bitcoin mines that have popped up in Georgia in the past, is there any way that Bitcoin's going to change the state, or are they so like they've like they're in bed with proof of state or proof of work, and that's it, right? Like there's no going
Because
back.
it's the first generation of that.
And they have no incentive to switch to their
That's
generation.
because what you want to do is you want to have a reward system for miners.
Okay.
And they are vested in the network so that you can continuously sustain it. Because when you earn a Bitcoin as a miner, you will only be able to redeem it 6 months later.
As in Bitcoin.
In Bitcoin,
Right? You have to keep Bitcoin in a different market.
You can convert Bitcoin to other markets, but effectively you have built it into the protocol so that it makes it very difficult, because it's a public network.
Okay.
And you don't want fraud, and you want to make it difficult to change transactions. So the proof of work is a very good way. That means that each time you have to put a block into a network, you have to climb Mount Shasta or some big mountain, take a photo and put it back. So you can't change anything unless you do that each and every time. So it's like an again. So Bitcoin is the problem that gives crypto back. Yeah. But everyone else now has learned from that and has moved to different kinds of services.
Do you feel like your industry will kind of push the problem back? Because I mean, I don't know too much about energy, but I think there's more.
Nuclear is more efficient, less polluting, and it allows you to pay much more money. That's why all the data centers now are trying to go for nuclear.
Yeah. So one of the situations that's been going on is Plant Vogtle just opened up a new reactor. Plant Vogtle opened up new reactors. The estimation is that each reactor could power 1.4 million homes or 8 data centers.
Yeah.
So each reactor only has 11 to 17 megawatts.
Yeah.
That's not that much.
That's not that much, but yeah. I mean, the amount of data power that you need is enormous. So I think there has to be a lot of.
Nuclear is not going to be the answer. It's too expensive and it's too slow.
And it takes 10 years to.
$46 billion to 15 years. And raise our power bills 10% for 1,000 megawatts.
Yeah. And it takes 10 years to launch one of those. 15.
It does decline the cost, right? Because this is like 70%.
Nuclear has never declined the cost. It's 15-year-old technology that
Well,
has never, is the one technology that has never declined the cost.
Well, they're going to have to build now that they've created train on workers and stuff.
So they said.
So one consideration on that is the Public Service Commission, who monitors all of the electricity costs for us, not for the data centers, have been approving Georgia Power to raise their rates 13 times since 2020. So our power rates are the most expensive in the country.
Oh, well, I'm not.
So when Georgia is bringing in data centers and crypto mines and things of that sort, we're paying for those costs because they're giving them rebates and discounts for their energy costs. But Georgia Power has to operate on a profit, so we pay for it.
Great.
Yeah, we're not. Where are we arguing different points? I'm not disagreeing with you there.
What did you say?
Oh no, I'm.
Right. So, well, and part of the reason we're all here today, right, is that data and crypto have become this thing that we're acutely aware of because we're paying $45 more than we were last summer and things like that. Both of these technologies are also kind of not growing anymore, so we have to discuss what are we make more energy efficient, and then we have to decide as a society, like, do we charge them? Do we say, cool, Bitcoin, you can continue to do your kind of work, but your energy rates are going to be 6 times as high as some other thing that uses proof of stake, right? Like, there's ways to incentivize them, but we also, and so when you go down and talk to people that do that on Sunday, they're going to be like, but I want to continue to use ChatGPT. So we have to be able to tell them that there are things that, like, so if a lobbyist for ChatGPT tells you that, no, it has to be this power intensive, so we're out of luck, right? Just be like, no, we know better, right? Because, right, one EOS is $7, right? And one, oh, sorry, these are prices. But anyways, like, there are ways to do this in a better, more efficient way. And technology is set up to the plate. It's just Bitcoin is lead. Right? I mean, well, maybe they have other reasons too, but so kind of like that's more really what do we want to decide to do? And we can't tell them to change if there's no alternative, but after the change. And so
What you could do is, for example, use Bitcoin sparingly for only synchronizing large batches of data that are using the latest blockchains.
Mm-hmm.
So that way you have a public check every couple of days, but rest of the time you're using the cheaper latest foundation blockchain. So you have a combination of hybrid chains, things like that.
Right, but there's no incentive for people to switch to that now because they can get their electricity super cheap, right? So they're great. All right, cool.
And also, I mean, if you talk to even people who are using EV cars, they think they're saving something. But they are powering up the EV cars using coal-fired furnaces.
That is not true. Georgia Power's grid is less than 15%, far less than 50% coal. And no grid is 100% coal. But let's say it was 100% coal.
Yeah.
And EV still goes a lot farther per mile on coal than gas, which is never going to grids are getting cleaner, more and more clean every day.
But that's what Chevron told me. I guess I said it off there last year.
Yeah, Chevron. Don't listen to that.
Don't listen to me. Okay.
That's not a lot of us.
Okay.
I think you yesterday.
Yeah. I went to the headquarters there. That's what they were saying. They spend more on their
Yes, just keep driving the gas car. And that's what of course they would say.
So it's called it.
Is there a comparison that you know, like, that you did, like, tell me, like, how much would you produce compared to?
Any other?
Yeah.
So in Georgia, in rural, is the most expensive power plant ever built on there. We're not rich state. Why do New York build it? Or Illinois, or California, or any of the states that are located in Georgia? Are we really so progressive that we can imagine we're out from anything? We're not. Global profits. It only produced 2,234 megawatts. You could have built 4 solar plants plus storage. People care about basic farm growth for a fourth of that cost to get 2234 megawatts of power. For a fourth of that cost. So we're proud of the bonus for have a whole grid of alternatives.
Do you have a car? Do you have a car?
Yeah.
You should come to Georgia and talk with some of our people there. Yeah.
I worked in Georgia Tech for a while to practice the smart grid research.
Yeah, smart education, speaker, and others. Yeah.
So that question, more general question, maybe tied to two talks together. So one of the marvels of the transformer architecture in the LLM space was that it reduced all these natural language tasks to an engineering problem, no longer to something like understanding grammar, semantics, any kind of linguistic knowledge. Now, I guess engineering problems, right? They have ceilings. They have some kind of logistic growth curve that you're going to level out somewhere. So my question is for both crypto and AI, what are the constraints of the engineering domains? Where are we going to run out first?
Yeah. So the first way is to use something called a mixture of experts. It's called MOE. So instead of using these larger and larger models, train smaller models for specific tasks. So that way you can have a general practitioner who refers you to a art specialist or an analyst who is only trained on a subset. So the idea here is that then you have a very scalable model as opposed to these experimental models. So that's one option. The second is to fuse different types of models together so that you take the best of many different models. So for example, if you're trying to predict the price of a house, we have one model that looks at the zip code, one model that looks at the bedrooms, one model that looks at the quality of the furniture. All these models are small, but you can put together. So that way you can build smaller and smaller models, but they are very domain specific. So that's the engineering solution. The second is what is called context, because many of these problems are based on the amount of context provided. So the current approaches are very poor in terms of understanding what context is best. So if you look at search-based engines and use some of that technology, you can really give very good context to the LLM so that it does this sort of matching much more effectively. So a lot of people are working on many of these sort of ideas, but the big lure is building these very talented models that do everything. And that's not very strong.
And from my perspective, I don't see a really setting for the engineering perspective. For example, before the transformers, we think that the power field network was CNN is the best combination we have, right? But suddenly we have transformers that changes everything. So maybe in the future we'll have a new architecture that renovates the entire system. Yes.
So I think about this human brain spends on trying to learn the subject, and that's a lot less than what OpenAI is running. So, I mean, aren't we trying to just pretty much solve puzzles until we can kind of optimize down to at least where we're at in the human level? Or something, I mean, maybe not in that far, but we got a lot of mileage to go, right?
Right. I would say human brain is more complicated than we think. Right. We have experience of neurons over there. There's no way we can simulate the entire brain using the computation resources in our minutes. So I would say that we need to think smart. We have to simulate the entire brain, how the brain works, but think about how to transcend human brains, or how to harness this big data.
Yeah, and there's a common example, I'm not sure if you heard of that. It's called reasoning putting together. So the common puzzle is that Columbus went around the world 3 times. And on one of these 3 times he died. On which of those 3 times did he die? So large language models, unless they look at the history, they don't really know how to reason. Because we traveled around the world 3 times and died on one of those trips. Which one did you die on? So it goes and looks and finds the names and tries to manage the trip you're on. But it doesn't know that if you're dead, you can't go around the world, right?
It's like train of thought. So
Yeah.
so you can call that train of thought. Yeah.
So there's still those sort of problems that occur. You can't solve that thing that like a human being can do, right? You ask the primary schooler which trip of so that's the sort of reasoning that this sort of last 20 years is there.
Yeah. One for you, right? One for you. The OpenAI's Owen Reading.
All those, yeah. That's what they're trying to push together and put in all that. But they have used web search as well.
Oh, yeah.
Can't just you go and look up Wikipedia and find out the didn't say and find it and that. So that's how they
Yeah.
Yeah, you could try to ask this question to the main version of GPT-C.
Yeah.
So
I don't think they can solve it. Yeah.
that's right.
Yeah. But if you combine it with other stuff like web searches, you can immediately find the answer from Wikipedia when he died and which trip and all that. So you can do all of it. Yeah. And another important thing about this new AI technology is this whole idea of agents. And that's, I think, more powerful than ChatGPT. Because now you can have a specialized task that is done by somebody on your behalf who can all coordinate this sequence of orchestra of agents working together. So you can say, I want to go to Paris during the winter. It finds out everything about your trip, your trains, and also the local attractions and everything else, and orchestrates the whole thing. And that's where I think the biggest worry comes, because now people were saying AI will not take our jobs away, but with agents, most of our jobs will become very and that's the big thing that's going to come up in the next few years, is that there will be an agent that does everything. Stock trading, when you're driving, your car is being driven by an agent, your investment is done by an agent, your teaching classes through an agent, everything is going to be done by an agent. And what do we do?
Also, so many of the agent models are actually based on specific specific tasks. Like the agent, you want agent to analyze the stock market, for example, you can train foundation models based on previous step, and then you can ask the agent to analyze it.
So that's the biggest risk right now, is that all of us will be replaced.
Alright, do you have any other questions?
Okay. Well, I'm curious to both your thoughts on something that always rattles around my head is that we our power infrastructure from a transmission standpoint is quite so like putting that declaration rate, people use like could be roughly 15% just on transmission loans, like just getting if not more depending on where you are. And it's like the arguments of like how we generate more power, like we're kind of born part of that we're regenerating, we're not effectively transmitting there, and just getting more development. Like you guys see that any opportunity or like that focus there, it was like kind of missing.
I mean, there's a lot of losses due to transmission, right? Because you're having all the resistance losses, everything else. Yeah. I don't think that is in the long run. It definitely improve by 30%, but I don't think that help us. Yeah.
That's an interesting thing to think about, though, right? Because they always talk about that with food security too, right? Like we lose half our food in transit and stuff like that. So is that a good analogy to make? And
I think that's.
It's a really interesting. I like it.
It only gets worse when we have more generation as well.
So what I love about this is now I'm going to throw Patrick under the bus, and we're going to have a thing about transmission, and right, like we'll find that would be a really cool speaker. So thank you for that idea. Cool. Well, all right, it's getting late, but I would like to thank our two speakers.
I'd like to, oh my gosh, so many microphones. I'd like to thank everyone for the spirited discussion. I think it's really interesting. We have a lot of choices to make as a state, and so it's really good to get all sides
what is going on, so that way we can really start to understand what it is that we need to do the right thing. So thank you so much for being here, and thank you to our two speakers. Thank you guys.